Hello, I am Ahmad, and in this video, we are going to talk about amplification factor to the member imperfection. Assume that a member is initially imperfected and going to be used for an element, can be a column under a compressive force. And if you recall from the other video about the imperfection, um, the member buckling load is not changed, but the way that it buckles would be different. The more imperfection we have, the sooner buckling would occur. In this video, we are going to talk about a beam which is initially imperfected and to see how it affects the maximum stress inside the element. The effect of this imperfection is also called amplification factor. Let's do it. Assume that we have a cantilever element rigidly supported at point A and at point B is under the force P. But before applying force P, assume that the element is initially imperfected. Like the green dash line. And the tip, point B, is deflected by delta 0 initially. Remember that this delta 0 is very small and it is exaggerated here. It is not in the scale and it cannot be seen easily. It can be L divided by 1000. And the deformation of this element is called V0 at point X. Suppose that X is from left to right, from A to B, and V is displacement in the downward direction. And V0 at X is delta 0 times 1 minus cosinus pi x divided by 2L, which means that at 0, cosinus will be 1, and then V0 is 0. And at the end, cosinus p over 2 will be 0, then it will be delta 0. Now, after considering the initial imperfection, now it's time to apply the load P at point B. So this is the initial deformation of the member, and then we apply force P. Now, due to the force P, it starts to buckle if we increase the load until it buckles. So that is called at the end, for instance, delta. And at each distance of x, the total deformation is V0x plus V at point x. By equilibrium equation, at point A, we will have P in the opposite direction. And as far as we have force with the eccentricity of delta 0 plus delta, we will have the moment P times delta plus delta 0. To derive to the calculation, we need to cut and find out the internal bending moment at the distance of x. The initial deformation is already known, and after applying the force, the gray dashed line shows the deformation. Force P and bending moment P times delta plus delta 0. The distance from the origin is x, and here we will have the internal bending moment m at the distance of x will be minus p times vx plus v0x This is v0x, and the rest is v plus p delta plus delta 0. Now, as far as bending moment is in the same direction as v, we can substitute mx with ei, second derivative of v, minus p vx minus p v0x plus p delta plus p delta 0. I can substitute v0x with the given equation. Ei second derivative of v will be minus p vx minus p times delta 0, 1 minus cosinus pi x divided by 2l plus p delta plus p delta 0. I can expand the equation. Ei second derivative of x will be minus p vx minus p delta 0 plus p delta 0 cosinus pi x divided by 2l plus p delta plus p delta 0. And here I can just cross p delta 0 with minus p delta 0. I can bring this p vx to the other side of the equation. Ei second derivative of v plus p vx equals to p delta 0 cosinus pi x divided by 2l plus p times delta. If I divide entire equation by ei, it will be second derivative of v plus p over ei vx equals to p over ei delta 0 cosinus pi x over 2l plus p over ei times delta. And if you remember, we use p over ei to be lambda square. Now the equation will be second derivative of v plus lambda square vx equals to lambda square delta 0 cosinus pi x divided by 2l plus lambda square delta. So it's a second order, linear second order, non-homogeneous differential equation. To solve this, we need to find out the homogeneous solution from the characteristic equation and also non-homogeneous solution. For non-homogeneous solution, we have two answers. One is cosinus and the other one is a constant value lambda 2 times delta. First, we need to solve the characteristic equation. I write the homogeneous equation r square plus lambda square equals to 0. As a result, r will be plus minus I lambda. And from here, we can derive to the homogeneous solution, which is a sinus lambda x plus b cosinus lambda x. Now we have two functions for the non-homogeneous. I will write it down v2x and the other one v1x. v1x is very straightforward. We have another video about this type of polynomial solution in the differential equation series. So it is lambda square delta, and from here particular solution will be lambda square delta divided by lambda square, and it's delta. This is the solution for the first non-homogeneous answer or function. For cosinus, we need to solve the other way. It's a little bit different. second derivative of v plus lambda square vx equals to lambda square delta 0 cosinus pi x over 2l. So in this case, we need to rewrite the particular solution with constant values in terms of cosinus and sinus. So v particular 2 can be written as c1 cosinus pi x divided by 2l plus c2 sinus pi x over 2l. And we need to define the first and second derivative to substitute all in the main equation and find out c1 and c2. For this, v prime will be minus c1 pi over 2l sinus pi x over 2l plus c2 pi over 2l cosinus pi x over 2l. And then the second derivative minus c1 pi square 4l square cosinus pi x over 2l minus c2 pi square 4l square sinus pi x over 2. Now we need to substitute second derivative of v and the function of v particular solutions to the main equation. So instead of second derivative minus c1 pi square 4l square cosinus pi x divided by 2l minus c2 pi square 4l square sinus pi x over 2l plus lambda 2 times c1 cosinus pi x over 2l plus c2 sinus pi x over 2l. And it should be lambda square delta 0 cosinus pi x over 2l. Now I can factor cosinus pi x over 2l minus c1 pi square divided by 4l square plus c1 lambda square plus sinus pi x over 2l times minus c2 pi square 4l square plus c2 lambda square equals to lambda square delta 0 cosinus pi x over 2l. The coefficient of cosinus in the left side is c1 lambda square minus c1 pi square divided by 4l square, and in the other side it's lambda square delta 0. And for the next term for sinus, c2 lambda square minus c2 pi square divided by 4l square equals to the other side. We do not have any sinus, so it will be 0. From the second equation, we can have c2 equals to 0, or lambda square will be pi square divided by 4l square. From the first one, c1 can be written as lambda square delta 0 divided by lambda square minus pi square divided by 4l square. Now, if lambda square equals to pi square divided by 4l square, then c1 will be infinity. As a result, it's not going to be the solution. In other words, with this, we will find out what is the critical load, which lambda will be P over 2L and lambda square will be P square divided by 4L square, and lambda square is P over EI, so P critical will be pi 2 EI divided by 4L square, which is the critical load of a cantilever column. It's not the topic in this example. We are going to find out what is the stress because of the imperfection when we increase the load in the column. So as a result, C2 will be 0 and C1 will be lambda square delta 0 divided by lambda square minus pi square divided by 4L square. Now I can rewrite the particular solution for this part. Vp2x will be lambda square delta 0 divided by lambda square minus pi square divided by 4L square times cosinus pi x over 2L. So now we have the particular solution for the constant value, we have the particular solution for cosinus, and we have the homogeneous solution. V will be homogeneous solution plus particular solution of 1 plus particular solution of 2. V at x will be A sinus lambda x plus B cosinus lambda x plus particular solution 1 was delta plus lambda square delta 0 divided by lambda square minus pi square 4L square cosinus pi x divided by 2L. Now what kind of boundary conditions do we have here? At point A, V at 0 is 0. V prime at 0 is 0. And at point L, V is delta. These are the boundary conditions, and we have A as unknown, B as unknown, and delta as unknown. Delta 0 is a constant value because already we have the deformation function. I also write the slope equation, or V prime. It is A lambda cosinus lambda x minus B lambda sinus lambda x minus pi over 2L lambda square delta 0 divided by lambda square minus pi square 4L square times sinus pi x over 2L. Coming back to our boundary conditions, the first one, A times sinus 0 will be 0, so B plus delta plus cosinus 0 will be 1. Lambda square delta 0 divided by lambda square minus pi square divided 4L square should be 0. From the second equation, A lambda 0 and 0 should be 0. As a result, A should be 0. And from the third equation, A sinus lambda L plus B cosinus lambda L plus delta plus lambda square delta 0 divided by lambda square minus pi square divided by 4L square cosinus pi over 2 should be delta. Cosinus pi over 2 is 0, so this is gone. Delta and delta are crossed. A is 0 As a result, B cosinus lambda L should be 0. One solution is if B is 0, or lambda L can be pi over 2. If lambda L is pi over 2, then again we are coming back to calculation of the buckling force that we already know what it is. As a result, in this special case, lambda L cannot be 0. Otherwise, then if we come back to the Vx here, and we substitute lambda as pi over 2L, then lambda square will be pi square divided by 4L square, and then the denominator of this fraction will be infinity. So this is not happening, and as a result, B will be also 0. If B is 0, if we come back to equation 1, then delta will be minus lambda square delta 0 divided by lambda square minus pi square divided by 4L square. Now we have delta A and B. We can come back to our main equation Vx and rewrite it with the determined coefficients. So A is 0, B is 0, and delta is minus lambda square delta 0 divided by lambda square minus pi square divided by 4L square. And now V at x will be lambda square delta 0 divided by lambda square minus pi square divided by 4L square times cosinus pi x over 2L minus 1. So this is the deformation by respect of the force that is applied. And the force can be seen in lambda square that we already have. If we are interested in the maximum stress in this element, so initially we do not have P in the straight line. We start to apply the load when it is already deformed with the distance of delta 0. As far as the stress is a combination between the axial force, which is compressive here with the value of P, and the bending moment. If we increase the load, then it will deform more. And with the more deformation, we have more bending moment at the support. Assume that when we approach to the critical load, it's coming to the maximum delta. So the maximum displacement will be delta plus delta 0, of which delta is V at the length of L, which we already calculated, and it was minus lambda square delta 0 divided by lambda square minus pi square divided by 4L square. Now, delta max at tip will be delta plus delta 0 will be minus lambda square delta 0 divided by lambda square minus pi square divided by 4L square plus delta 0. I combine these two terms together, minus lambda square delta 0 plus lambda square delta 0 minus pi square divided by 4L square delta 0. And now these two are gone. I can rewrite delta max equals to pi square divided by 4L square delta 0, and I can apply the negative sign to the denominator, pi square divided by 4L square minus lambda square. For a column with the force of P at the tip with rigid connection or rigid support at the other end, critical force is pi square EI over L effective square. And L effective in this case for Euler calculation is pi square EI, it is 2L. So power by 2 4L square. Also, we assume that lambda square is P divided by EI. If I substitute this value of lambda to delta max can be calculated according to pi square divided by 4L square, delta 0 divided by pi square, 4L square minus P over EI. And if I divide numerator and denominator by pi square divided by 4L square, then it will be delta 0 divided by 1 minus E divided by pi square EI over 4L square. Pi square EI divided by 4L square is P critical, or we can call it Euler load. So then it is delta 0 divided by 1 minus P over E. In different codes, for example, in timber codes in Europe, Eurocode 5, you will see this amplification factor. Also in the calculation of concrete columns, also somehow some factors relevant to this value is also considered. So we have delta max and we can calculate the maximum bending moment. Maximum bending moment can be calculated according to E times delta max, and it will be P delta 0 divided by 1 minus P over P. If P equals to Euler load or it buckles, then M max will be infinity because it is now buckled. If it's less than that, then we can see that it's E times delta 0 divided by a positive value. Now, the next phase is to calculate the stress in the element. So the stress can be calculated according to the force divided by area as far as it's compressive. So it's negative plus minus moment divided by section modulus. So it will be minus P divided by A plus minus. Now maximum moment is E delta 0 divided by 1 minus P over Euler force times 1 over section modulus. So sigma can be written as minus P 1 over A minus plus 1 over 1 minus P over PE times delta 0 divided by W. Now it would be easier if we go through a numerical solution for this example. Suppose that we are going to have circle hollow sections 88.9, 6.3, and S275, meaning that the yield stress is 275 megapascal. Assume that the length of the column is 5 meters and delta 0 is L divided by 1000. First, it's better to calculate what is the critical load. P critical will be pi square EI over 4L square. This is also Euler force. Pi square 210 gigapascal times moment of inertia of 1.40210 power by 6 millimeter power by 4 divided by 4 times 5000 millimeter power by 2. 29 kilonewton. Now assume that the applied load is 1/3 of this value, which is 10 kilonewton. So sigma will be minus 10,000 Newton times 1 divided by area, which is 1635 square millimeter, minus plus 1 divided by 1 minus 10 kilonewton divided by 29 kilonewton times delta 0, which is 5000 millimeter divided by 1000, and then section modulus is 31.55 10 power by 3 cubic millimeter. So sigma will be minus 6.12 plus minus 2.42. It will be minus 8.54 megapascal, and also if we minus 8.54 will be for negative negative, and the other one will be minus 6.12 plus 2.42 minus 3.72. Now it is good if we can calculate what is the maximum load that we can apply to this element before it yields. For that, we can rewrite the equation of sigma, and instead of sigma we can use yielding value, 275 megapascal in this case. Determine the maximum E at material yields. So sigma will be minus P over A, and as far as we are going to calculate the maximum value, we need to go with the negative sign. Minus P divided by 1 minus PE times delta 0 divided by W. And as far as it's going to be a compressive value, so this sigma will be also negative. So I can just multiply by the negative sign, and sigma will be P divided by A plus P divided by 1 minus P over P times delta 0 divided by W. And from here, we can just multiply by 1 minus P over PE. So it will be sigma minus sigma P over PE equals to P over A minus P squared divided by APE plus E delta 0 divided by W. And now I multiply this with APE. We will have sigma APE minus sigma AP equals to PE minus P squared plus PAPE delta 0 divided by W. Now I can write it in descending way, so it will be P squared plus or minus A times sigma minus PE minus A PE delta 0 divided by W times E plus sigma A PE equals to 0. So this is a polynomial of second degree, and we can substitute the values from the cross section and find out the loads. If we continue with the same cross section, so A will be 1635, sigma will be sigma yield, which is 275 megapascal. Boiler load is 29 kilonewton, delta 0 is 5 millimeter, and W is 31.55, 10 power by 3 cubic millimeter. What else? Have everything, and I can substitute all to the equation. E square minus 1635 times 275. So this is Newton. As a result, I have write PE as Newton 29,000 minus 1635, 29,000 times 5 millimeter divided by 3155, 10 power by 3 cubic millimeter plus 275 megapascal times 1635 square millimeter times 29,000 Newton. Coming back to our equation, so we factor this negative here. This should be positive value. So the load P will be two solutions, 28,491 Newton or 457,647. 28.5 kilonewton and 458 kilonewton, of which the minimum value is the answer. So P will be 28.5 kilonewton. Now, if we increase the delta 0, or if we increase the force, then the amplification factor will be higher. It is obvious. Now we can compare this result with for example, Eurocode to check how it works. For this, first of all, we need to go through Eurocode and find out what kind of cross section do we have. In this example, we use the elastic section modulus. As a result, we are in the elastic design. We can check what kind of section do we have. First of all, we need to go through the Eurocode 3, and from table 6.2 we can find out what kind of section do we have and what kind of buckling curve we need to consider. So here in this example we used S275 and it's a hollow section, and we used hot finished, so the buckling curve will be A. So buckling curve is A. Now we need to find out what kind of imperfection we need to consider from table 5.1. So for buckling curve A, and elastic analyzes, E0 over L is 1 over 300. So E0 over L is 1 over 300. And as far as L is 5 meters, 5 meters divided by 300, it will be 16.67 millimeter. This is representing delta 0. Coming back to our equation from here, if I apply this delta 0 to this equation and solve it one more time, delta 0 is 16.67 millimeter. A is 1635 square millimeter and W 31.55 10 power by 3 cubic meter. And then what else do we need? Sigma at yielding point is 275 megapascal and boiler load was 29 kilonewton. So the load will be from here 27.375 kilonewton and 476 kilonewton. So this is not the answer. As a result, the maximum load that we can apply is 27.375 kilonewton. This is the theoretical solution based on what we derived. Now let's check from Eurocode what would be the maximum load that we can apply. So here we used curve A. Lambda is calculated according to square root of 1635 square millimeter times 275 megapascal divided by n critical, which is 29,000 Newton, 3.94. It's very slender. Practically, it is not a good cross section for this length, but just for the calculation, it is worthy to have a look on that. Then we can calculate phi. 0.51 plus alpha is from the table, 0.21 times 3.94 minus 0.2 plus 3.94 over by 2. 8.65. As I said, this is really not a practical example. Now we can substitute this to chi factor. So it will be 1 divided by 8.65 plus a square root of 8.65 power by 2 minus 3.94 power by 2, which will be 0.06. And then from the other terms in Eurocode, and calculate the maximum compressive load that it can resist. So NBRD will be G times A Fy divided by gamma M1. So this value is 0.6, 1635 square millimeter, 275 megapascal divided by 1. If we go with 61, then this value will be 27.43 kilonewton. So here we can see that the answer is almost the same, 27.375 kilonewton, the same as Eurocode calculation from here. Almost the difference is 27.375 divided by 20. So it's less than it's 0.2%. It's really nothing. So here is how the amplification factor would affect the buckling or the maximum capacity of a column, and the curves in Eurocode is produced by the same concept. For example, in Eurocode 5 for the timber structure, we will see directly this amplification factor effect in one of the terms, if I recall it correctly. We went through the amplification factor and we discussed about the initial imperfection. This is usually called bow imperfection in codes. And we could see how the initial imperfection would affect the maximum capacity of the element. Also, we checked with Eurocode, the same principle is applied according to the maximum imperfection provided by the chapter 5 in Eurocode, and we compared the results and they are almost identical. I hope you enjoyed this video and see you next time. Thank you. Bye.